Swayam Prabha. Digital India. Educated India.
It is a pleasure to be able to participate in this seminar. I regret that it is remotely, given the wonderful introduction of all the capabilities on this campus that Professor Rangaswamy just gave. It's clear that IIT Madras is a center that all of us in the process systems engineering domain should be visiting. I've been asked to talk a little bit about the evolution of PSE and the research agenda of this field in this era, I should say, of digitalization. I suspect that, anytime you're asked to talk about evolution, I think the organizers had in mind history, and I guess they always call upon us graybeards to provide history. So I'll try to make it a little bit more forward-looking than just history. What I'm going to do is very briefly summarize PSE accomplishments for you, talk a little bit about the application challenges, and then get into the digitization wave and try to relate how that fits into how PSE has evolved. And one of the questions, of course, one should ask is digitalization a evolution or is it a revolution? And I hope you will agree in my conclusions. Having set that stage, we'll then very briefly recap 4 areas that are really critical for the digitalization move. And it certainly shouldn't surprise you that that's data models, software architectures within which these technologies have to live, and then the computing innovations to really make all of this feasible. So first of all, let me begin with the legacy part. As you are well aware, it's been some 60 plus years of PSE contributing to the chemical process industries. We don't really need to recap that in detail this afternoon. There are some 3 very strong review papers that I would direct you to that I show on the bottom of the slide, one of which just appeared earlier this year. As is pointed out in those papers, there's really basically 4 main areas of accomplishment that PSE can point to with great pride. The first has been in the area of process flowsheet modeling and optimization. The second is process synthesis, of course, process control, scheduling and planning. And most importantly, in all of those areas, these developments have not just existed on paper. They have actually found their way into commercially available and accessible tools. And that's very important for the field. Now, I'm going to just very briefly recap the key features in each of these technologies. Process flowsheet modeling is now a tool used at the undergraduate program. So very clearly, it has permeated the chemical engineering discipline. It started in the 50s with the sequential modular architecture. Over time, constraint handling, flowsheet optimization using SQP approaches, and of course, most importantly, equation-oriented alternatives have developed. These things have only become possible because of the developments in physical property modeling. Without the model libraries, the databases, the ability to predict properties of mixtures, flow sheeting process simulation would be much retarded. And of course, since those initial waves, group contribution methods and other groups of materials have been characterized with the PhysProps package. So there was some years ago that Dr. Lakshmanan at one of the FOCAP-D meetings made the bold statement that the sequential modular form of process flow sheeting has now achieved universal adoption. If it did then, it certainly has now. In the area of process control, really the field has moved forward with data-driven methodology first and foremost, initially in process monitoring using statistical methods, basic feedback control, advanced controller building blocks, various data-driven tuning and performance monitoring systems, and most recently, of course, recent being the 80s, model predictive control, principally linear, but increasingly with nonlinear applications and with and without state estimation. The paradigm is seen in most textbooks in process control, essentially the use of a model to predict how a process should be adjusted over a horizon. And then, of course, the classical solution of only implementing the first period and then repeating the re-estimation process. And again, a paper back almost 20 years ago by Chin and Bagwell reviewing the field back then already claimed that, model predictive control is widely adopted in refinery and petrochemicals. And certainly it will be increasingly used in other sectors, such as, for example, the pharmaceutical industry. The other area of great importance has been process synthesis. Again, a number of problem categories that have been addressed, from heat and power networks to separation systems to mass exchange networks, attainable regions. The approaches have really spanned the range from heuristic or constructions or thermodynamic construction like pinch method, superstructures, math programming to solve these superstructure optimization problems, and actually some very interesting work in recent years in systematic enumeration, which boils the superstructure problem down to a smaller set of structures. I think it's fair to say the industrial impact, particularly the heat and power network side, has been substantial. Really hundreds of papers published and continue to be published with illustrating how important heat integration and power integration can be. I would point to you a very interesting application by my colleague's group. This is Professor Rakesh Agrawal. They just published a paper jointly with colleagues from ExxonMobil, in which they demonstrate that by using systematic methodologies, they were able to improve the classical crude oil distillation through a retrofit that has 15% less energy and 16% less CO2 emission. Illustrates, that significant progress can be made even in industrial installations that one would think have already been so well polished that there is not much more room for improvement. Clear example where PSE can still have an impact. Planning and scheduling has also been a very active area, one that I've been personally interested in. And it has ranged from multi-period MILP applications to refineries, utility systems, water, and so forth. Likewise, in the scheduling area, lots of really exciting progress in terms of how to handle these complex combinatorial problems. A very nice review paper published back in 2014 that sort of recaps some of the key ideas. However, of course, the field has been moving forward, and we, had welcomed recently the book on scheduling that was produced by Professor Maravilias. Continuing to show that there is significant work yet to be done in this important area. Now, as I mentioned, while it's important that the field has made these contributions and published, it is even more important that these tools be implemented in practice. And it's really noteworthy that there have been many important software implementations now available to industry. And many of these have been really involved expensive and long-term developments. For example, in the flow sheeting area, when you think about it, Aspen plus Origins are with an energy, Department of Energy and MIT project launched in the mid-70s. The GPROMS work started in the mid-60s at Imperial, and both of those packages are now actually licensed and supported, in the former case through Emerson, in the latter case recently in Siemens. On the process synthesis area, many applications, particularly in heat and power. On the separation train side, a few commercial packages, but lots of academic and in-house work. And of course, in the advanced process control MPC area, all DCN vendors offer capabilities in those areas. The scheduling planning domain is really such a broad domain. It goes much beyond process systems. As we practice it, it really pervades all manufacturing. So there's plenty of commercial packages available. And I would just mention one that one of my colleagues started some years ago, Advanced Process Combinatorics. Their software has been actively used in industry for the past 20 years. This is an area where there's continuing challenges just because of combinatorial complexity. So I'm sure we will see more progress as time progresses. Now, in the area of PSE applications, of course, in the past and in the present, our focus has been to support design operations in the chemical process industries. It is interesting to question, what are the challenges in the future? And I would point you to a recent U.S. National Academy of Studies, actually just published earlier this year, in which the panel reviewed what these grand challenge areas are. And I just list them here. They range from carbonization of energy systems, to sustainable engineering, to targeted and accessible medicine, to flexible manufacturing and circular materials. And again, the panel recognized how important tools are to the future of chemical engineers if we are going to make progress in those areas. Now, if you look at that list, and I'm sorry that I had to take it off the screen so you couldn't, cogitate about it, but the key features of these grand challenges areas, they all involve large-scale systems. They all require an integrated systems perspective. They're multi-scale in temporal and spatial dimensions, always involve uncertainty and models parameters of data, and all inherently require some quantitative risk assessment to support these system level decisions. And most importantly, of course, they also require in-depth knowledge of the application. And certainly that opens them up very nicely to our PSE community, which is, of course, populated by chemical engineers who have a very good understanding of energy systems, healthcare related issues, and so forth. Now, as I mentioned, the panel has also had the wisdom to recognize that one needs to worry about tools that allow one to address problems in these grand challenge areas. And it shouldn't surprise you that the tools that they listed, everything from data science and computational tools to modeling and simulation to sensors and even novel implementations of instruments like lab on a chip or plant on a chip, all point to the areas that are really core to chemical engineering. And again, it shouldn't surprise you that within the data science computational tools, certainly AI and data science applications are prominent. In the modeling simulation area, the wonderful word of digital twin shows up in the list, and we'll talk about these topics as we proceed. A related study, in which I had the pleasure to be involved, addressed PSE applications of pharmaceutical manufacturing. This is a study on innovations in pharma manufacturing that was issued a year ago, and it points to key areas in which PSE applications will be relevant. Of course, in the area of drug substance, handling new synthesis routes and therefore the new models and separation trains that will come with them, process intensification on the drug product side, formulated product design really a key area for PSE, as I'm sure Professor Gandhi will remind us when he speaks to you. Innovative areas like additive manufacturing, certainly continuous manufacturing, that is the transition from the traditional batch to continuous in all areas really of pharma, including freeze drying, where one is trying to change the system as it currently exists and shown in the upper right-hand corner of my slide to something that is a bit more modern, continuous, and so forth. And of course, the recognition that all of these things can only happen by virtue of automation and control technologies, and that includes sensors, sensor networks, control system design, condition-based monitoring, and all related areas that are really PSE intensive. There's included in there a discussion of innovative manufacturing networks. Again, something that is core to PSE, where we're not just at batch and not just at continuous, but at highly automated hyper-production lines, which require integrated control and scheduling. The idea of modularization is really important to the industry, and it has interesting questions in terms of control system design, safety, and security. There is even work going on in portable point-of-care systems, which would really, in some sense, be a prime challenge for PSE, because such a system really has to operate with real-time release. That is, when the dosage is produced, the patient can consume it without further quality control. Of course, the word digital twin again appears in the pharma innovation study as well. So I invite you to look at that document in more detail. I think you'll be amazed at how central PSE is to really innovations in pharmaceutical manufacturing. So the recurrent themes in the National Academy studies, and certainly in many other studies on the future of manufacturing: increased digitalization in the generation, management, and use of data, the effective use of this data to build high-fidelity models, the use of such models, in this context referred to as digital twins, to guide both the design and to support real-time operations. These are really key parts of each of these studies. And of course, the digitalization and digital twin theme appears in all of them. And, you know, us academic cynics could well say, you know, are these just buzzwords, or does this really represent real change? And, you know, what new challenges does this digitalization wave pose for PSE? The assertion I would make is that from the perspective of PSE, digitalization is not a revolution. Rather, it is a very logical evolution of PSE. And it will be achieved and is being achieved by exploiting advances in computing information technology, which is what our community has been doing since its inception. When you look at all of the areas where progress has been made, it has always been made by pushing the envelope of what you can do with the computing information technology available at that period in time. Now, in order to support that assertion, I would like to kind of recap for you the couple of key development paths that PSE technology has followed in its 60-year history. And I would say path A is that of mathematical model and analysis. And historically, the applied math sort of legacy is certainly attributable to the faculty at University of Minnesota, Eris Amundsen and followers. And this path has featured an emphasis on mechanistic models of exploiting the numerical and optimization of the time and actually enhancing and developing them further. Analysis of the mathematical properties of these algorithms and models, both convergence, stability, uniqueness, and so forth. A very key part has been nonlinear model prediction, so parameter estimation from experimental data. And the key in that domain, in that historical period, was really the data was expensive and sparse, and so one had to be parsimonious in how you use that in making your model agree with reality as much as possible. In this development path, performance really was measured in terms of solution quality, model fidelity, and the solutions were applied offline. So speed was not a primary concern. Accuracy was. And of course, the domain was product and process design first and foremost. The second development path was really the data-driven path, even back in its incentive. And it was really of industrial origin. It was our industrial colleagues who worried about process monitoring and control. And the features of this path was initially make decisions from data using statistical methods, then build simplified data-driven or linear models or surrogate models to help make those decisions. the solutions required were in real time, or at least in a time scale that made them relevant to the dynamics of the operation. And this was, a theme in which data was abundant. The concern was really more about the quality, the reliability, and the dispersed nature of the data. For this development path, the performance requirements were really speed of solution. There was a recognition that the solutions would be updated frequently. Look at, linear model predictive control. And so high accuracy was not critical. However, speed was. And the applications, first and foremost, were in process monitoring and control, and then gradually expanded to model predictive control, scheduling, and planning, where actually one could make use of relatively simple linear or perhaps mixed interlinear models. Now, the third path, which is the one that we're embarked with now, the digitalization digital twin, I would view to be a logical merger of paths A and B. It builds on PSE legacy, and it again takes advantage of advances in computing, data storage, access to data at high speeds that we currently are enjoying. And the features are pretty obvious. We deal with large and diverse data flows from multiple sources actually occurring at different frequencies and even different levels of accuracy. High fidelity models for design and operations, that's where the digital twin comes in. This high fidelity is obtained by combining the mechanistic with data-driven components, and that's where we get the hybrid models. And then given what we have available in terms of data and models, really key component is always model predictions, dealing with the effects of uncertainty, both structural, parametric, and the input data. And of course, for the digital twin concept to be relevant, the digital twin has to change as the process is changing, and therefore model and parameter updating, adaptation using whatever methodologies are relevant, for example, Bayesian methodologies, is really, really important. Here, the speed of solution does matter, and particularly on the operational side, I want to be able to support decisions both at the short term and at the longer time scales. And again, a decision that is relevant to the modern era has to have quantitative risk assessment. And the application domain, of course, is all the domains that PSE traditionally covers, as well as the grand challenge areas that I referred to earlier on. So given that perspective, then the question is, what more needs to be done? And of course, we always need to do more. We need more capabilities in all of the key areas of process systems engineering. Approaches in dealing with diverse data and its management remains a key area for research. Effective methodology for building these hybrid models, a software architecture where building and integrating these kinds of models into system-wide models can be enabled. And as always, we need developments to increase computational efficiency and scope. It is just inherent to PSE that we're always stretching the boundaries of the size of systems and problems that we can deal with. And I will briefly touch on some developments in each of those four areas. First of all, in the data area, I'm sure you realize that one of the blessings and curses of data in the process and related industries that the data categories are very broad, both time series and static information, traditional information about streams and unit operating variables, but also information about the status of the resources being used to carry out manufacturing. So status of instruments, of units, of control systems, all constitute important input information for us to make decisions. Static information, of course, always is there, even traditional information such as set points. information about the units and instruments being used, the calibration data that was used, and so forth. The data types are very wide, from discrete, when you think about the status of a control system, you want to know whether it's available, running, or faulty. So there are really 3 states, but there are also point values. Increasingly, there is use of spectral analysis tools to get composition and other measurements. So using Raman, near IR, infrared, the entire spectrum. And that involves a different type of data than we traditionally have used. And of course, increasingly, the use of imaging to get size, shape, intensity, color are really very, very important to developments in manufacturing. And by virtue of us being able to handle data at higher flows, I think the image processing is going to become even more important over time. Now, given this diversity, the question is, how do you manage that kind of data? And certainly, industry has addressed this by having multiple data repositories, both laboratory information system, the traditional process historians, information resident on PLC, MES systems, ERP systems. They have all been implemented in practice. Unfortunately, they have sort of existed as islands of data. And in recent years, there's been a lot of effort in terms of integrating these data into something called data lakes. I think the practice so far has shown that while that is a significant step forward in terms of making this information accessible, it is really not integrated in the sense that it's easy to access all of the data relevant to a given project that may reside in one or more of these systems. And so there is significant work to be done yet in terms of effective data management systems. And of some of the challenges that exist are the fact that there's all kinds of variation in the data quality and data quantity, data fusion, there's integration of diverse data types in order to allow us to do things like state estimation, where the data inflows into the state estimation model comes from different sources at different frequencies with different error bars on it. How do you take that into account? And most important, the issue of data provenance. This is an area which one has to give credit to our colleague, Professor Venkata Subramanian, who really raised issues with regard to data provenance, metadata, context being presented together with the data so as to make it actionable. And there's been some initial work on how to organize that kind of information so that we provide a framework for data gathering for projects as they are executed. And there's been some, as I mentioned, initial work in this area. I just give you a little example from some of the work that was carried out by our groups at Purdue. And this was in the context of managing the data associated with carrying out analyses of pharmaceutical products. So this is an FDA project, and when the project involved sort of comparisons of quality metrics of various generic products produced by different manufacturers. So the key part was having our pharmacy colleagues collect information on products in the market using the established critical quality attributes and how they're measured. So this is an example of a application where one seeks to establish the province of dissolution testing. And of course, that test has a standard procedure that is required to be followed. And one can model that standard procedure through a graph with tasks and subtasks that identify all of the materials that must be prepared and how, all of the activities that are required and using what resources. And then, of course, then also establish a link to the actual raw data repository, which will allow extraction of the relevant information. So a simple example, each of the tasks and subtasks have parameters, The net objective of having done this now is if there is a question about the validity of a test result, you have the complete provenance of how that number arose, who did it, where it was done, and what procedure was followed. I would suggest that if we really want to capture the provenance and the context of the information that our PSE methods will be using, we need some kind of structures that will allow us to do something like this. Now, this is rather primitive. I'm sure there are much better ideas that will come forth. Let me next talk about the second area of PSE relevance, which is that of methodology for building and adapting hybrid models. And certainly the notion of hybrid models is not a new thing. One sees components in the literature appearing already in the 1990s. The principal difference, as is pointed out in a very nice review paper by Sansana and partners, co-authors, they sort of looked at the development of hybrid models as sort of a balance beam, where when you think about it, in the path A of PSE developments, the heavy weight was on the mechanistic side. The data-driven was pretty thin. In the big data era, the reverse was happen. And of course, the challenge is to balance that appropriately. And fortunately, we now have lots of choices to be made in that area. We can choose the level of detail of the mechanistic component. We have a range of AI, ML methods available. And, we have lots of ways of structuring these kind of hybrid models. And I borrowed this simple block diagram from Sansana et al. It was also repeated to some extent in a second review paper by Professor Liu and colleagues. If you look at them, the green component provides input to the mechanistic component in the simplest sort of hybrid model, where the data-driven component might be a machine learning model that captures kinetics, which is then fed to the reaction engineering model. You could have the reverse, where the machine learning approach essentially bridges the gap between the mechanistic model prediction and the reality of the process. And of course, you can have parallel structures where each model component contributes data to the overall predictions. Okay, and just as a simple example, I'll show you a pharma application. So this is on the left-hand side, we see a continuous process from going from feeders to a tablet press, and the unit operation in the middle is a roller compactor. And that unit operation essentially consists of a mechanical device that has two parts: a compactor, which takes powders and compresses them into a ribbon, something like you can think of a chewing gum ribbon, maybe a bit larger. And then the second part, which is a two-stage mill, which chops that ribbon up into granules. And the inputs for this kind of model are, shown on the center bar. Things like feed screw, roll gap, roll pressure, so forth. There are inputs for the mill section as well, in terms of screen size, screen gap even, and mill speed. And there are outputs, throughput, ribbon solid fraction, ribbon thickness. And some of those inputs really serve as additional inputs to the mill model, which then produces size distribution. This is an example where you have aspects of both the serial and parallel structure. Relatively straightforward model that has a mechanistic component that deals with the mechanics of compression of powder and producing a ribbon. A model that takes into account the material relaxation that occurs when the material leaves the rolls. And of course, a machine learning milling model. One could certainly write population balance models with a breakage kernel for this part of the process. But of course, breakage kernels are typically data-driven models, and people have worked on using machine learning to make those models better. So it's just a simple example of a hybrid model, and clearly there will always be parts of the process where our ability to write mechanistic models with sufficient fidelity is going to be challenged. And so if we really want to track the process closely, we're going to need to have machine learning components to it. So in the area of hybrid models, again, there's now been several review papers in this area. So I will just recap what these are. Certainly, model identification is really a key requirement. We have to basically build a machine learning model, and we have to come up with the parameters of the mechanistic component. Validation is always a key issue. Increasingly, people are starting to worry about building hybrid models in a data sparing mode. The key here is to bring the hybrid model up as quickly as possible, and so you don't have an enormous set of data to work with. So how can you build an effective model that is data sparing? Of course, the hybrid model needs to track reality, which changes. Therefore, strategies for adaptation of the model are important. I maintain that any model that is used to make decision needs to have prediction of confidence or credible regions, depending upon, whether you're a Bayesian or a frequentist statistician. The enablers for building these models are really flexible software environments. And this environment needs to be transparent so that these hybrid models can be built, managed, and adapted, and facilitate really combining these models into system network models. The grand challenge problems we looked at basically all involved large systems, networks, whether they're electric grids or processes or supply chains. It's always networks. And of course, we're always stretching the capabilities of our numerical and optimization tools. So one needs to have a software environment where you can bring in the latest and greatest developments in these areas and do that without having to substantially re-engineer your software. Just by way of example, I thought I would show you a development you may not be familiar with, which is the IDEAS platform. This is a development launched within the U.S. Department of Energy. It involves several academic partners in addition to the national laboratories. I think colleagues at CMU, at West Virginia University, and even Notre Dame are involved. And the goal of this project was really to provide advanced PSE capabilities to support design optimization new process. And the key goal of this effort was to address the weakness in existing systems, the existing system being the conventional process simulation packages such as Aspen Plus, and then the algebraic modeling languages such as GAMS that provide functionalities that are very desirable from an optimization point of view. The simulation packages typically don't do well in optimization because, to a large extent, the optimization occurs through the black box framework. It's complicated to add new standard dynamic models or to modify the existing models, which are often hidden. And of course, uncertainty quantification is difficult within those packages other than simply Monte Carlo. On the other hand, the algebraic modeling languages really are not set up for building reusable process models. They don't really make it easy to integrate model libraries, properties, those sorts of things that we're used to having in building process models. And they're challenged in terms of handling multiple time and length scales. And so the idea of the IDEAS project was to try to address some of those weaknesses by basically putting together a extensible equation-oriented process system and library of units, take advantage of the open source DOE-funded Pyomo algebraic modeling language, And its current capabilities are, to a large extent, have achieved some of these, addressing some of these weaknesses. So it is an open source platform that can use state-of-the-art solvers. It makes it more convenient to build libraries of new dynamic unit operation models and properties, and provides most recently support for superstructure design and optimization under uncertainty. Now, the primary applications that have appeared so far have all been, of course, in integrated energy systems, which should not surprise you given the sponsor. The IDEAS platform basically does the usual unit, process unit, and physical property models. However, it lends itself to being extended in multiple dimensions. And I think the most important is that it seeks to provide multiple functionalities, process optimization, conceptual design through the superstructures, process dynamics, uncertainty quantification, data reconciliation or state estimation, AI, ML methodologies integrated, and even surrogate models integrated, and even enterprise optimization through suitably structured model. And of course, using the Pyomo kind of framework to allow ready access to the latest and greatest developments in the optimization domain. Okay. The key points here I would like to leave you with is that this is an exciting development. However, it is not without its challenges. By virtue of creating a Python-based framework that allows you, convenience in building and accessing open models, it really is a platform that's suited for a user that can do that. This is not something you can, turn over just for routine use, as you might with an Aspen plus simulation and an existing library of models. The building of equation-oriented models, which is key to the IDEAS project, requires expertise. Although IDEAS does offer some really nice modeling constructs in terms of assembly of material and energy balances, nonetheless, building robust equation-oriented models is not, a skill that most researchers have without digging into it to some extent. The other key problem with equation-oriented models, of course, is the initialization. Whether it's solving a set of nonlinear algebraic equations or it's actually initializing, an optimization model, how to do that effectively is still, a research issue. And currently, this is done through trial and error, through use of simplified models and lots of tricks that practitioners build up, which create a barrier really for broader use. Now, the IDEAS project is, being continued. They're adding capabilities in terms of implementing process control application. And certainly, when you think about it, state estimation and MPC are really optimization problems, right? So the solution of these optimization problems is readily at hand using the IDEAS construct. However, tying them to DCS and all those practicalities have not been developed as yet. Certainly the capabilities for building hybrid models are there. Surrogate modeling, AI, machine learning component access is there. So I would say the digital twin, as we idealized it, to really build and use them, all the components are at hand, but the IDEAS team is still going forward to try to demonstrate that. Now, just in a very small way, I'd like to point you to another development that's really borrows to some extent, from the IDEAS project, and that we've carried out with my colleague Zoltan Naj at Purdue, and that is to build PharmaPy, a Python-based tool for simulating pharma processes, which takes advantage of this idea of text-based construction of applications with lots of flexibility and user control by virtue of the Python environment. Open source lends itself to access to extensive libraries, allows convenient data manipulation and using of data manipulation tools, numerical methods to do dynamic modeling, to do optimization, and to carry out various supporting tasks where one can access Python-based tools. Now, the application that this was focused on under FDA support was really to address batch, continuous, and hybrid operations, and so allow one to mix and match these unit operations and be able to model these kind of processes. General features are object orientation, ready, an easy way of adding new models, providing a convenient framework for doing the estimation. I should point out that the one key limitation is that we use the sequential modular strategy with some refinements of how to handle dynamic models. It, by virtue of using the SM approach, it is restricted to doing optimization using black box and gray box strategies. These are just examples of software environments that are needed in order to address, the hybrid model and its use in both design and operations. I would say the existing simulation packages really don't lend themselves to the full use of the hybrid concept, although one has to give credit to the teams involved that they are trying to head in that direction, but they're not there yet. Having now a software environment that allows you to build hybrid models and to assemble them into networks, then the remaining question is, how to address the computational challenges that these models involve. And if you think about it, in order to make the hybrid digital twin kind of concept practical, we have to deal with some important computationally demanding subproblems. Parameter estimation, training of machine learning model, even doing Bayesian modeling or Bayesian hierarchical modeling in order to handle uncertainty. The optimization of large-scale systems, stochastic programming. All of these are very computationally demanding. Our community is used to tackling these kinds of problems using decomposition and algorithm engineering methodologies. I think we will need to do much more of that in order to be effective. Certainly, our community has not ignored high-performance computing architectures that are available. I would say, however, probably not to the extent that we could. There is work to be done in exploiting that. And I just like to also point out that there is a new generation of modality that's appearing that you may have seen that's getting a lot of attention, both technically and politically, I'm sad to say, and that is the area of quantum computing. And I would just call to your attention a very interesting perspective papers that were just published earlier this year by David Bernal and some colleagues, both from academia and from industry, in which, they raise the community's visibility of the potential of quantum computing. This is not a new development. It's been around since the 1980s. The key issue has really been demonstrating that indeed the use of QC will accelerate some of the computational tasks that we want to address. In the review paper, Bernal et al. Point out that for chemical engineers, there's really three areas of potential application. The number one is the computational chemical molecular simulation area, which shouldn't surprise you too much. The other is discrete optimization, and the third is machine learning. And they point out in the review paper, I won't reiterate for you, some of the initial work that's being done in this area and what one might expect down the road. There are still, lots of limitations. So this is really kind of bleeding edge development. There's limitations on the size of hardware realization that currently exist. There are a fairly small number of accessible QC hardware installations that researchers can use, although there are software emulations which can be used to test ideas. And in general, the basic software ecosystem is not well developed as yet. However, I think it is important that the PSE community be engaged and aware of developments and attempt to integrate it into our toolkit. It is really very exciting, and we have high expectations of developments in this area. I might add that my colleagues and I at Purdue are so optimistic about this area that we've actually recruited David to join our faculty, and he will later in the next year. So let me just conclude this exposition by reminding you that I've tried to sell the notion that digitalization is really a logical extension of PSE methodologies. There are significant challenges, even though it is a logical extension. There are significant challenges that arise both in, as I mentioned, the management of data and knowledge, the building and supporting and use of high fidelity hybrid models, developing software architectures that make it easier to build such models and maintain them and use them, particularly at the scale of applications that are highlighted in the challenge problems of the National Academy study. Interesting work to be done in algorithms and strategies for handling multi-scale system, and of course, exploitation of advanced computing architectures. My personal, of course, bias is also to call your attention to digitalization in the healthcare area. I'm happy to have observed that we have a number of papers in the conference that will address developments in this area, and I certainly look forward to learning more about them. So with that, I'd like to conclude my presentation and thank you for your attention. And depending upon whether Raj and the committee will allow me, I'll be happy to answer any questions.
Thank you, Professor Eclitus, for the 30,000 feet view of PSE's past and its future challenges. Since we are about 5 or 6, 7 minutes, I'll take a couple of questions from the physical audience present here physically, before also giving an opportunity to the people who are raising these questions online. I would request you to first introduce yourself before asking the questions.
Hi Rex, this is Ilmun. Can you see me?
Yes, I can.
Okay, good to see you again after Phoenix. And thank you very much for your intuitive talk, and then a very good big pictures about the future. Thank you very much. Well, I'd like to mention about the process safety and industry. This issue is also very important, and there are numerous problems that this new technology can be applied. But unfortunately, there are not many new young professors in this area. Well, how do you think about the future of the process safety area in PSE?
Well, that is what's called a leading question, right? Definitely process safety has to be integrated into all of that we do in design and in operations. I'm happy to point out that at Purdue now for several years we've had a process safety center that is supported by a couple of dozen companies, and several of my PSE colleagues have projects in that domain. I think it's just simply one of the requirements that have to be built into everything that we do in design and operations. It's integral to it, and a lot of the methodologies that we're addressing, for example, in condition-based monitoring, is really both technically to make the process continuous, but also to ensure that the process is safe. And safety in this case is both from the human perspective and from the environmental perspective. So I have no doubt at all that this is an important area. But I view it as being integral to everything that we do. It is not an add-on or something you do at the end of the pipeline in order to solve a problem you've created upstream.
Are there any questions? Any more questions? There are no online questions, so we'll open it out to the people.
Hi, it's François Maréchal from EPFL. So very nice talk. I have a question about the use of all our models. Because at the end, I think that we could perhaps also add the decision support in the picture, which would perhaps then introduce another difficulty that it's a multi-criteria approach, which means that the models should be able to give us access to a lot of different criteria and not only one behavior of the system. So going from simulation to optimization to finally multiple domain where there are or observation of the search space to some extent. So how do you see this dimension of finally being able with models to generate collections or domains of solutions?
Let me see if I interpret the question correctly. I think I view models, and in particular the hybrid modeling concept, as really as a mechanism for knowledge retention. So we really, if it really is a digital twin, it isn't just the data support. It is a decision support tool, but it is a way of, in a compact form, capturing what we know about the system, and that knowledge has to, include the economics, the sustainability aspects, all of those things that go beyond simply the one dimension of delivering an economic solution. I think this is, it's a multi-criteria world that we're living in, and the model has to be able to accommodate that. I think that the kind of technologies that are coming along and use of hybrid models really facilitate that much more than the traditional, a model did, because we couldn't really capture everything within the mechanistic model. But now I think we have a better chance. However, we still have the related issue, which is that of interpreting what the model says, what it's telling us, and that becomes a little bit more opaque with the machine learning component added.
Thank you.
I don't know if I addressed your question, but I certainly talked around it.
Yeah. It was going in this direction. So models that can feed models, in fact, and machine learning as well, which is something which is then going perhaps to allow us to explore the possibilities, in fact, more than just getting one solution.
Mm-hmm.
Thank you, Professor Reclitus, for the thing. In the interest of time, I think we'll move on to the next speaker. We have Professor. So give a Professor good hand.
Very good. Thank you again for the opportunity, and I regret very much not being able to witness all of the great things that are happening at IIT Madras, as Professor Rangaswamy claimed. So I hope the rest of you will check it out and make sure this was just not hyperbole.
Validation. He's talking about model validation, and it's perfectly so.